morning, class.
Good morning, ma'am.
Today we're going to talk about finding the area of an irregularly shaped region. I'm sure you are aware that this is the second question that gave birth to calculus. You're already past the first one. What was the first question, if you remember? The first question that started calculus off? Or I'll help you recall. There are two types of calculus, right? First one is differential calculus. Good, Joseph. The second one is integral calculus. And finding the area of a region is an application of the second type of calculus. No? The first one answers finding the slope, right, of the tangent line to a curve. This second calculus, integral calculus, its specific application is finding the area of an irregularly shaped region. The problem lies in the term irregular. Because if it were a regular region, a familiar region, I'm sure you know how to get the area.
Yes.
Right? Okay, let's see. Let's prove that yes. Jonalyn, you said yes quite forcefully. Okay, so if the region were of a regular, familiar shape, you'd already know the formula of its area. Right, Jonalyn?
Yes.
If it's a rectangle, Miss Jonalyn, what is the formula for its area?
It's length times width.
Yes, it's length times width. And from the area of a rectangle, we may derive the area formulas of the other shapes. For example, this one, the square, right? A square is a rectangle, okay? Except that its sides are all of the same length. So if an area had sides all of length S, what would be its area? Rachel?
The area of a square is S squared.
S squared. If the sides are of length S, then yes, the area will be S squared, right? Now, we all know that half of a rectangle is a triangle, right? So, its area this time is going to be half the area of a rectangle. So, for a rectangle, if you have length times width, this time we call it, what is this part? The base and the height. So if it's base times height instead for a rectangle, then for a triangle, it would be, Joseph, please?
The formula is base, 1/2 base times height.
Half of base times height. That's right. Okay. And now more of the triangles now. If you put one triangle on top of another, so that coincident sides will have the same length, what you get is a trapezoid, right? A trapezoid. And the area of a trapezoid is based on the formula for the area of a triangle. Two triangles with the same height. So for a trapezoid, what is that familiar formula? Who remembers? Jonalyn again? Okay.
The area would be base 1 plus base 2 times height divided by 2.
Okay, you'd have the first base, the second base, times the height, all over 2. Yes. Okay. Now, another familiar figure. We're done with those with the straight sides. Now we deal with something with a curve. Now you have a very definite idea, of course, of the formula for this region, for this shape. Area of a circle. Area of a circle. One of the gentlemen at the back. Emmanuel.
The formula for a circle is pi r squared.
Pi r squared, where r is the
Radius.
radius. Thank you. Pi r squared, the radius would emanate from the circle to the edge of the circle. And if that is your r, then yes, your area is pi r squared. Okay? So these are for familiar figures. What if it gets a bit less familiar? Something like this. There's no single formula for the area of something like this now. This is a combination of a square or a rectangle and part of a circle. Yes, maybe a semicircle, right? Now, area is additive. If you do not have a single area formula, you can split the region, get the individual areas, and the total area will be the sum of these two areas. Okay? For example, this one. In architecture, this is known as a Norman window. You have a rectangle topped by a semicircle. Usually if your window is shaped like this. Okay, sometimes it's a semicircle, sometimes it is a triangle on top. Okay? However, in this case, if we're just after the area anyway, okay, you may split so that what you have is one area over here for a familiar shape now, rectangle, and this one, the area of a semicircle. Now, from the earlier recitations, you know both the areas already. So you just have to get each one, add them up, and there you have the area of the entire region. Area is additive. Okay. If it's not familiar, what's the lesson? You break it up into familiar parts. Okay. My question for you now is, how do you get the area of something like this? Doesn't look familiar, right? What did we say earlier? If it does not look familiar, you break it up into parts which would look more familiar. And when we say familiar, we mean you know the formula for the area. Okay? So in this case, if we're going to reproduce it on the board, you may have several ways of finding the area. How many shapes do you see?
4.
You have part of a circle, maybe 1 or 2 different circles. You have something that looks triangular because you have that diagonal over there.
Yes.
And then maybe you have something rectangular. Okay. Now what I would like to do next is maybe ask 2 of you, 2 volunteers, reproduce the shape on the whiteboard, and then on your own, divide it into your familiar regions. Can we do that? May I have 2 volunteers? Joseph and a lady. Let's have Chrysalis. Yes, please. I'll hold it over here so you can reproduce it. And then on your own, you don't have to have the same answer. In other words, don't look at each other's work. And then divide into familiar regions, please. There. You might want to do it on your desks as well. And don't worry if your divisions are not the same as your seatmates. Yeah, Joseph, that's almost... Here you go. How many regions? You have 4. Now let's see. You may compare your work with those on the board. Now for Chrysaline, we have how many regions? Huh? Chrysaline gave us, 2 triangles over here. So there's 1 region, area of that region, area of the second region, 3rd, 4th, 5th, 6th, 7th. 7 regions. So area for Chrysaline is A1 plus A2 plus A3 all the way up to A7. Now let's look at Joseph's work. Joseph, has 1 long rectangle down here for the first region. He splits it into this triangle as a second region. This one looks like, it's like 1/4 of a circle. Okay, A3. A4 is half of a smaller circle. Okay, so Joseph's area is A1 plus A2 plus A3 plus A4. Okay, now how familiar are they? Area 1, Area 2, Area 3, the 3 are triangles. Familiar because we know the area formula. Okay? A4 and A6 are rectangles. Okay? So we know the area formulas as well. A5 is 1/4 of a circle. You already know the area of a circle, so you just divide into 4. And this one, you just divide into 2. Okay? So this is correct. And over here, it looks different. Right? A1 up to A7, this one only has 4 regions. But is it any less correct? This one is still correct. Area is additive. You may divide differently, but the sum of the areas should still be equal. A1 is a rectangle, A2 is a triangle, A3 is 1/4 of a circle, A4 is 1/2 of a circle, all of whose respective formulas, area formulas, you know. Okay? So it's not a problem as long as you can split into familiar shapes, right? And as long as you have an idea what these dimensions are, because then it's just a matter of plugging into the formula. Okay? Now, is it still that friendly for a bit more complicated shapes? So very good, class. Are there any questions with this shape?
No.
None.
So this is an easy shape.
Yes.
Okay, good. This one must still be an easy shape. Where's the yes? The loud yes this time. Huh? It should still be an easy shape, right? Because you still have the straight edges. So when you get your pens and divide, you can still get out your rectangles, your triangles, your squares, and all of whose formulas you still know. Right?
Yes.
Yes. Something like this now. Okay. Here we start getting the rub. This one down here is straight.
Yes.
At least there's one straight side. Over here, we hope it's straight. But then up here, you start getting squiggles. And squiggles, they don't count. Even if you have the area formula for a circle, the squiggles still don't count. Right? Meaning, they're not familiar in that sense. We don't have a formula in getting the area of a region whose sides are squiggly. Whether it's one side or several sides. Okay? So over here, you have two sides which are straight, but then we're still being a bit kind. We're not letting all sides be squiggly. But here, just the top and the bottom may be. But still, the problem holds. No matter how we divide these two lower areas, it looks like it's going to be impossible to divide it into rectangles, triangles, and the familiar shapes. So this is where the question will come in. How do you get the area of an irregularly shaped region? You think you can get the exact area, class?
Yes.
Yes? How? Let's see. Just some ideas. Maybe you'll get the same ideas that Newton and Leibniz got when they were figuring out the question themselves. If you do not have the exact formula, what's the next best thing? Derive. Something may be easier. Yes? Ramon?
The next best thing to do is to approximate.
The next best thing is to approximate. That's correct. If you don't have it exactly, then you try to approximate, you try to estimate. It's not quite a circle, it's almost a circle, so maybe its area is. It's not quite a rectangle or a triangle, but it's close to one, so maybe its area is. Right? And then you approximate. But then in a lot of cases, whoever is asking the question may not be happy with an approximate, so he or she will strive to do better than an approximate. He does a first approximate, improves it, gets a second approximate, improves it, gets a third one, a fourth one, until he says, I think that's it. And that was how they did it for the area of an irregularly shaped region. Not different from how they did it for the slope of a tangent line. Okay? Now let's see if we can mimic what was done.